In this video, we'll review proofs. We'll give examples of non-constructive proofs, proof by cases, direct proof of an implication, proof by contraposition, proof by contradiction, and finally, how to disprove a statement. First, proof by cases. When we conduct the proof by cases, we consider exhaustively all the possible cases that can occur and show that the claim would hold under all such cases. We make sure that our cases are mutually exclusive most often, and what we mean by that is we try to make sure that all the cases cannot happen simultaneously or even pairwise simultaneously. We're going to use a proof by cases in order to show the following claim. Among any three integers, there are two whose sum is even. In order to do so, we will use the pigeonhole principle. But first, we need to recall that any integer has a parity, which is whether it's even or odd, and that if two integers have the same parity, their sum will be even. First, to apply the pigeonhole principle, we have to consider what our pigeons will be. So in this case, our pigeons will be our set A, so let our set A be the set of any three integers. Our holes, or our set B, will be the set 0, 1. Now we need a mapping from A to B, and this mapping, F, will be the value of the integer mod 2. This will turn out to be the parity of the integer, because if the integer x is 0 mod 2, that means it's even, and if it's 1 mod 2, it's odd. So since we have three integers that are being mapped into two parities, and both of those sets are finite, by the pigeonhole principle, there exists at least two integers with the same parity. Okay, so now we need to show how that's sufficient to show our claim, and we have to break it down into cases now. So the two cases that we need to worry about, the first case is if both integers are even. In this case, without loss of generality, we'll just call these integers x and y. And because they're both even, there exists k1 and k2 respectively, which are integers, such that we can express x as 2 times k1, and we can express y as 2 times k2. Now when we consider their sum, we will have 2k1 plus 2k2. When we factor, we will get 2 times the sum of k1 and k2. And since the integers are closed under addition, we know that k1 plus k2 is an integer, and this implies that x plus 1 is even because we have written it in terms of 2 times an integer. Now let's consider the case when they're both odd. Once again, without loss of generality, we're just going to call them x and y. And there exists k1, k2 in the integers such that we can write x as 2k1 plus 1 and y as 2k2 plus 1. When we add them, we are going to get 2k1 plus 1 plus 2k2 plus 1. And then we can see we can factor out a 2, so we're going to be left with 2 times k1 plus k2 plus 1. And once again, we observe that k1 plus k2 plus 1 is an integer, since the integers are closed under addition. And since we have expressed x plus y as the product of 2 and an integer, x plus y is even.